أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. This is lecture number 3 of electronic devices and circuits EDC by myself. In continuation with the previous two lectures, third lecture is the final lecture, I think, in the semiconductor material and the PN junctions. So something more about the semiconductor PN junction. Silicon at temperature 0 degree Kelvin acts as an insulator, but at higher temperature, here E minus sign is stand for electronics, stand for electron, so I will use this one. It will be read as electron. So silicon at temperature 0 degree Kelvin acts as an insulator, but at higher temperatures, electron gain thermal energy, occasionally breaking away from the bonds and acting as free charge carriers. So it means the silicon is an insulator only at temperature 0 degree Kelvin, that is equivalent to minus 237, I think, something degree centigrade. So it means if at room temperature there must be the silicon will not be an insulator, because at room temperature, maybe at 25 degrees centigrade or 22 degrees centigrade, there will at that temperature the thermal energy will apply on the silicon, and of course some of the covalent bonds will break and charge will become free. So let's see. We know semiconductor material doping. We know what we have done so far. I think this is the review of the previous class. We know semiconductor material. Yes, we know semiconductor material, how it is get. We know the doping process. We know the N and P type semiconductor material so far. The impurity, the doped atom. Impure atom is basically the dopant atom. If doped at 1 part in 10 million, silicon can alter the band structure sufficiently enough to change the electrical properties of the material. It means how much this the pure silicon is important. The pure silicon is can have impurity atom 1 part in I think in 1 billion. So if this slight impure atom is very tiny amount of impure atom is added, then it is sufficient to change its electrical properties by making the covalent electrons free. Okay, as we have seen this one before, this is the simplified N-type material. Here, the electrons are the majority carriers. So it is noted that the N-type material, although has a large number of free electrons, yes, it has a large number of free electrons, is still electrically neutral because the number of positive, yes, it has a large number of electrons, but the number same number of positive atom will also exist, because if the electron is removed from one silicon, it means the electron is free. It means the electron from the silicon outer shell is free, is away from its outer shell. In consequence of this one, the silicon atom will have more proton than its electrons orbiting around it. So the nucleus of the silicon atom will have positive charge because it has more proton than the electron. Hopefully you understand. So it is noted that N-type material, although has a large number of free electrons, it is still electrically neutral. Why it is neutral? Because we know the number of electrons, okay, the negative charge we have at the same time, but at the same time due to we have positive charge on the nucleus. So it is electrically neutral. No current can flow from here to here. It is still electrically neutral because the number of positive charge protons in the nuclei is still equal to the number of free and orbiting negatively charged electrons in the structure. So there will be no flow of current, but we can say yes, there is no flow of current, but still we have plenty of free electrons. The nuclei is not free to move. Nuclei has positive charge, but it's not free to move. The free to move is only the electrons. So what we can say, that this has capacity, this has capability, this has tendency to make flow of current through it very easily. Okay. Finally, we come to know that PN junction can be formed. However, during this process, a thin layer of potential barrier is formed, which has voltage of 0.7 for silicon and 0.3 for germanium. And this potential barrier makes PN junction an insulator once again. We did this thing before. I think this slide is just for is just the review of the previous topic. Okay, one more thing. We know the intrinsic semiconductor means a pure semiconductor. Okay, and similarly, if the pure silicon is doped with impure atoms to change its electrical properties to create n-type and p-type material, then this material is called an extrinsic material. Intrinsic material is pure semiconductor. Extrinsic material is maybe n-type material, p-type material. I mean the material where we dope with some impure atom. Hopefully you understand these two terminologies. You must be very clear. Let's move. Now it is time to understand more about this PN semiconductor. We just have studied on the abstract level, on the basic, and uh, and we studied very simplified atomic structures of the semiconductor so far. So we need to study something more. So now be ready. First of all, we know that the electrons are the free carriers, and we know the flow of electron is basically the flow of electron means the flow of current. Okay, but there might be some confusion because the holes are having positive charge. Can it bring current? Yes, the holes can bring current, but at the same time we are saying that holes are basically the protons, the charge on the protons. Okay, so we have to see how holes can contribute. We know the how the electrons contribute in the conduction, in the flow of the current. Now this time we will understand how the holes is contributing in the conduction, means in the flow of the electron. Let's see. It is clear that if an electron is excited, then its covalent bond breaks and consequently leaves a vacuum on its original atom, which is called a hole. Hope you understand about the vacuum. As we have seen here, as we also have seen this figure before. So this is the silicon structure. Each silicon is sharing one of this electron. So two electrons are being shared here. But here, maybe due to some reason, one electron is moved from this covalent bond of this silicon atom. This is the parent atom of this removed electron. And of course, if this parent atom now will have more proton than the electron, so this will develop a positive charge. So the positive charge will be there. So that's why it is said vacuum. If the electron is removed, there will be a vacuum or a void on its original atom, parent atom. This is called hole. So we call this one is hole. This atom will have positive charge. Okay, that is, if an electron is freed, then there will always be an electron hole pair generated. If electron is removed, so we can see here, if electron is removed, so it means soon the electron is moved, the same moment the positive charge will also be generated, the hole is also be generated. So we can say if an electron is freed, then there will always be an electron hole pair, electron and hole, it's always be generated. Now on the other hand, similarly, on the other hand, if this electron or any electron falls, come close to this hole and falls inside this hole, so this electron and this hole, the pair will diminish. The pair will annihilate it. It will be destroyed. It will be completely destroyed. There will be no any charge. So similarly, whenever the freed electrons come across and falls into the hole, then there will always be electron hole recombination. So this process where the electron and hole come close and neutralize each other. So this process is known as electron hole combination. Okay. Now take a structure of silicon here. This is a pure silicon. There is no impure atom. There is no free electron. There is no holes. So this is pure silicon, and we know the each silicon is sharing 2 electrons. Okay. At time t0, let's suppose there is no free electrons, but at after that time, if an electron is moved, then we know that consequently a positive charge will also establish at this silicon atom. So at this time, so we divided it into two different and into steps of sequences in time. So at this time t1, we have the covalent bond 1. In this covalent bond, we can see only one electron is sharing, so the other electron is not sharing because the other electron is removed, it is away, and the hole is created. Okay, so the covalent bond 1 is broken here. We should read something here. Let us understand the movement of holes inside the crystal. Assume due to some reason a hole is created at covalent bond 1. Yes, at covalent bond 1 at some time before t is equal to t1. Okay, before t is equal to t1, the hole is created. Okay, due to some reason, due to thermal energy, due to photon light energy, or due to any reason. Okay, okay. Now after this time, if at bond 2 an electron is released, okay, if electron is released at bond 2, so this electron falls into the covalent bond 1 hole. This if the this if for example if I take this one, if the covalent bond 2 is broken and one electron is freed, then we assume this electron falls inside this hole. So so this covalent bond will become complete. So this covalent bond 1 is now complete because it gains one electron, and that electron is released by this silicon atom. So this silicon atom, because it has removed one electron, so it will establish a positive charge at bond 2, and we can see that at bond 2 the bond is broken. Okay. Now at time t2, if an electron moves from bond 2 and recombines with hole in bond 1, the same we have seen here. I explained this process before. So now let's suppose one more event at time t3. So silicon 3, this silicon, this covalent bond 3 releases one electron, and that electron falls into the covalent bond 2. So now we can see the covalent bond 2 is complete, it's sharing. But because this covalent bond 3 has removed one electron, so a positive charge will establish in this silicon atom. So we read again. Similarly, at T is equal to T3, an electron leaves bond 3 and falls into the hole in bond 2, making bond 2 complete. Or on rewinding this root, the root of the hole, it can be realized that one hole has moved from left to right. So now if we rewind this process, it was nothing. There was nothing. So at this time, one hole was established at this location. Then after this, the second hole, this hole we can say is moved from position 1 to position 2 and from position 2 to position 3. So we can say that the holes is moved from left side to the right side. Okay. So on rewinding this route, it can be realized that one hole has moved from left to right. So this movement of hole from one point to another confirms that holes also contribute in the flow of current. This is an important property to analyze current flow through the semiconductor device. Please remember this property. Remember this property. Holes also move within the crystal lattice. So it can also contribute in a small amount of current, not the big amount of current, on a small amount of current. Okay. So remember, now we found the clear understanding of holes in the conductions. So hopefully you understand this one. This is very important property. We already know that electrons are the responsible for the flow of current, but now we have seen the holes are also responsible for the contribution of the current. Okay, but of course the electron, the flow of the current due to hole is very small. Some more topics: majority and minority charge carriers. So we have to understand very clearly majority and minority charge carriers. So the intrinsic silicon, if applied with thermal or light energy, the effect of this would be equal concentration of free electrons and holes generated by thermal energy. Yes, we know. We already have discussed. Let's suppose another figure with a simplified figure. If this is a silicon crystal and this silicon crystal is not at 0 degree Kelvin, okay, this one is at room temperature. So it might be possible there are some free electrons and at the same time some free holes will also exist. So we can see here holes. The holes are you. This is the charge on the silicon nucleus, and this is the free electron. This should be very small than this one. Okay, but figure just is a simplified figure. So we can see at room temperature, a silicon crystal can have holes and the electrons. Okay, so the same is written here. The intrinsic silicon, if applied with thermal or light energy, the effect of this would be equal concentration of free electrons and holes generated by the thermal energy. Yes, there will be equal. There will be equal number of free holes. There will be equal number of free electrons and the holes. You understand? These charge concentration is small enough. This charge concentration is small enough to ignore the conduction of current at room temperature. That is right. Also, this effect is discouraged, and while manufacturing, it is minimized. So this is not a good property that at room temperature any crystal has holes and electrons. It's not a good property. So during the manufacturing, it is tried to minimize the number of holes and number of free electrons at room temperature. But anyway, uh, there there will always be a number of holes and electrons. Might be in very few numbers, but there exist. Hope you understand. So please remember this one. We will try to complete this one. The Okay, if we keep this one as minimum as possible, so we also say that these are the in a very small number, and this we can ignore the current due to this movement of these free electrons. We just ignore. Okay, this is not enough to measure it, but there exists. Okay, so now the question is how we can make this silicon structure a conductor, how we can change its property. We already have studied about the doping. The doping is the process to increase the concentration of carrier charges in the semiconductor crystal. So this will not increase the carrier charges. Instead, during the manufacturing process, we try to minimize it because it's not a good sign. So how we can increase the carrier concentration is by the doping process. Okay, in the semiconductor crystal, after doping, the crystal is known as N-type and P-type material. The N-type has high concentration of free moving electrons, and P-type has high concentration of holes. We have done these things. So if we dope, for example, this is an N-type material, N-type silicon, it means the phosphorus atom has been added, doped inside this crystal, so there will be free electrons. So doped free electron. This minus. So remember the difference between this one and the previous one. This red negative sign is used to represent the doped free electrons. So all these minus signs are the free electrons, but these are the whole. Remember, these are this electron is due to the thermal effect, and this is the positive charge on the silicon nucleus. So remember, there are different charges, but the important thing is that if we dope these charges is without the doping material, but if we dope with n-type material and dopant, so the free electrons will be this, and these free electrons are really responsible for the flow of the current. It's responsible for the conduction property of the n-type material, and this conduction property is due to these free electrons. Okay, so the n-type has high concentration of free moving electrons, and if you make the p-type, the p-type will has high concentration of holes. Remember, p-type will have high concentration of holes. So I have shown only for the n-type material, and I think you can study the p-type materials in the textbook or in the reference book, or maybe I have included in the next slides. I am not sure. So we understand these two figures. You have to differentiate between these two figures. These are the charges generated by the thermal energy, and the dopant material causes the concentration of the free electrons. The red is the free electrons. Okay. Now move next. This is the same figure here. So at the same time, we can say that for N-type silicon with phosphorus as doped atoms, after releasing electron, the proton on phosphorus nuclei will be greater than the electrons orbiting it. Nuclei, if it releases one electron, then it means the number of proton is one greater than its number of electron orbiting around the atom. So it means the nuclei of this phosphorus will have positive sign. We must have to incorporate that positive charge in this figure. So now we have this n-type material, same material. So as we know, the free electron is here. It means this causes the positive charge on the nucleus. Okay, so these are the nucleus atom. We can see I have shown the equal number of free electrons and the equal number of the holes, the donor atom. So these are the donor atom. Here in this case, the phosphorus. Phosphorus releases one free electron, and in consequence of this, it develops, it establishes a positive charge. Hope you understand this one. So this is the real figure of the N-type material. It's not exactly real figure, but it is approximately. Thus, a positive charge will be on its nuclei, but no holes are generated. Remember, these nuclei are the charge. These electrons are free electrons. The electrons is removed from the outer shell of the phosphorus, and it's wandering from here to here, moving from here to there. But this bond, this is phosphorus bond, which is still making a covalent bond with the neighboring silicon atom. So this nucleus, this atom as a whole, is charged with positive sign, but this atom, because it's a big, it's a large enough, then this electron is of very small size, and this phosphorus atom is firmly bonding with its surrounding, with its neighboring silicon atom. So this cannot be moved. So what is the important point here? The electrons, the donor which donates one electron are free to move, but the donor atom has positive charge, which is strictly firmly bonded, and it's not movable. So the current due to this positive charge is not is it does not exist. Hope you understand. I read again, but this is a very important property. There's a positive charge will be on its nuclei, but no holes are generated. Holes are not generated. I have seen before, I have shown before in this figure, there is a hole and there is electron. Okay, but this hole, this hole is this, since the nucleus of phosphorus is firmly tied with the silicon by covalent bond, so this positive charge on the nuclei is unable to move, and therefore no contribution of current due to this positive charge. Hence, the actual N-type silicon crystal looks like in the end figure. So this is, we can say, for the time being, we can say that this is the actual figure of the N-type material, and we can see the charges, different charges here. If we furthermore analyze, you can see here that this was the free electrons. Okay, and this is here, this is the also free electrons. So free electrons is increased. Mainly the free electrons is this minus, is the free electron is the minus charges. Okay, but this electron is also free, so the both electron will combine with each other. I mean, the contribution of the current will be due to the free electrons, the and also due to this electron. Okay, next, the concentration of free electrons in the n-type, the concentration of free electron, this one in the n-type silicon is denoted by Nn, where N is the negative number, and means the number of electron, and N subscript is used for the n-type material. Thus, Nn is determined by the doping concentration and not by temperature. So this Nn is dependent on the doping concentration. It's not by the temperature. By the temperature, this one is only. So not by temperature. All the holes in the N-type silicon are generated by thermal ionization. You can see here this hole, thermal, due to the thermal, the holes, the electrons and the holes are generated by the thermal effect. So the holes which are moving, the electrons which are moving, is due to the thermal effect. But the concentration, the concentration of the electrons we can increase for the better conductivity by increasing the doping material, the amount of the top material. and top material is mainly responsible for the free electrons here, although we have some other charges. We can see here the electron majority carriers is electron here, and the minority carrier is the holes. As we seen before, this was the hole. So this is mainly the the electron, the flow of current is due to the majority carriers, is not due to the minority carriers. Let's we study something more. Finally, we know that in the n-type silicon, the concentrations of free electrons will be much larger than that of holes. So finally, we got this one, and where we can see, not can see, but we understand that the free electrons is much number of free electrons is much larger, much greater than the holes. Holes are these are the holes. So concentration of free electrons will be much larger than the that of the holes. Hence, electrons are said to be the majority charge carriers and holes the minority charge carriers in n-type silicon. So the conclusion is that majority charge carrier is minus the free electrons. There also be minority charge carrier which is holes. So holes can also contribute in the conduction, in the flow of the current, as we discussed before, but it is very less amount, but we cannot ignore in some applications. So soon we will study more electronic devices, so we can understand the role of the main majority carriers and the roles of the minority carriers. We can see how this minority carriers, the flow due to this hole is not good for the semiconductor devices. But we should now understand the n-type material has majority carriers and also the minority carriers. Okay. On the other hand, for p-type silicon, this I shown only for the n-type material, but we can understand similarly. You can go through it by yourself or do it self study. So on the other hand, for p-type silicon, holes are the majority carriers and electrons are the minority carriers. The concentration of the minority electron is temperature dependent in this case. Okay, so in n-type, the concentration of the minority carrier is temperature dependent here, and for the p-type, the concentration of the minority carriers, which is electrons, is also dependent on the temperatures. Okay, hope you understand this one. Now, the energy levels importance in semiconductor material. This is the next topic. So we should understand this one is also important. The energy levels. Okay. In the atomic structure, the, the nucleus, the protons, the neutrons, the electron shells. Electrons we know in the inner shell, then the middle shell, then the outer shell, and we know the important shell is the outer shell, that is we call as a valence electron. Okay, so we know the as the how it's moving because of the the energy levels. Electrons has different energy levels at it different shells. For example, as the electron, those electrons which are away from the nucleus and orbiting around the nucleus, it has highest energy. Okay, so in the atomic structure, there are different energy levels for the orbiting electron on each atom. Yes, it has different energy levels for different shells, even for different materials, and the highest energy level is associated with the electrons on the outermost or the valence shell. So valence shell electron has higher energy. If the valence shell electrons has a higher energy, highest energy, it means it is likely that the higher energy electrons will move away from the nucleus. So this is important. The energy levels of the outer shell electrons are different. For example, for the germanium, silicon, and gallium arsenide materials, we will see it. Let's suppose overview of the energy levels in different shells, energy bands. The as the band is close to the nucleus, this is the vertical graph. Vertical line shows the energy level in electron volt. So this is the first band. Maybe I just as an example, this may be the innermost band, energy band. Then this is the next higher band. This is the next higher band, and this is the conduction band. Okay. So what is the conduction band? If electron outer shell moves free, becomes free, then it means it is in the conduction band. Okay. So which electron will move away from its parent atom? Which one? That one, the electron which will have the highest energy. So the highest energy will jump from its covalent shell, and it can jump to the conduction band. So this is the understanding of the conduction band, the outer valence shell band, lower shell band, lowest shell band. And this is just an example. It is not the actual figure. So for this figure shows the conduction band for insulator as an example. For an insulator, rubber is an insulator, glass is an insulator. So for this type of material, the insulators material, the outer shell electrons, yes, they have all outer shell electrons, but they need to move from this level of energy to this level of energy. The difference I found in the book is the energy gap is greater than 5 electron volt. So the this is the valence shell energy level, and this is the conduction band energy level. So the difference between this one and this one is greater than 5 electron volt. So it means the any electron that has to move to the conduction band, it should get more than 5 electron volt energy so that it can jump from here to here. And this is the gap is very high. This is not possible for the insulator outer shell electrons. So it has not capability, it has not tendency, it has not uh, enough energy to cross this gap. So none of the electron, under normal conditions, none of the electron can be jumped from here to here. So it means the insulator's conduction band is having no free electrons. If it has no free electrons, so it's not a conductor. It cannot conduct current. It cannot conduct current. So because there is no electrons in this band, it can none of the valence electron can reach, can can jump such a high energy level. So this is an insulator. It cannot be. This is a perfect insulator. Okay. So this is the example, and now we understand the energy level. Okay, because the germanium, silicon, and gallium arsenide. So for silicon, more energy. Okay, wow, it is more energy. Okay, this is the uh, energy gap diagram for the semiconductor materials. So we can see here the for this semiconductor material, the conduction band is closer as compared to insulator. Here, the conduction band is closer to the valence shell band. So it says that it can jump some electrons, not all. Some electron can jump from this energy level to the conduction energy level. Okay, it can jump. So how much energy it needs? For germanium, the to overcome this gap, the germanium free electrons should require 0.67 electron volt. 0.67 electron volt it will require. And so if this is the germanium, and if we apply enough energy greater than 0.6 electron volt, then this germanium outer shell electron can jump easily from here to, okay. For silicon it is 1.1 electron volt. Okay, for silicon it is higher energy we need to jump, and for gallium as arsenide it is more higher. So what we see here for germanium, if for germanium atom it requires less energy. It means for the germanium semiconductor it is easier to make free electrons because it requires less energy. But for silicon it is 1.1 electron. So for the silicon it needs more energy to cross this energy gap, and for gallium arsenide it is more than the silicon. So for silicon, more energy required to become conductor than for the germanium. That's right. Similarly, an electron in the valence band of gallium arsenide requires more energy than silicon and germanium to enter into the conduction band. Okay, so this requires more energy. This is tougher. Okay, this is very easier at, so we can easily excite electrons with the germanium, but we need more power, external power to excite the gallium arsenide. Okay, so example of the conductors in the conductor, the band, conduction band and valence shell band are basically overlapping with each other, and there you already found some free electrons in the conduction band. So there is no need to create doping or to create some special material. These conductors, for example, copper or the silver or the metal, it has already free electrons in its conduction band, so it's already a conductor. It's a pure conductor. Hope you understand. So one electron volt, the energy is the one electron volt is equal to 1.6 times 10 raised to the 19 joules. The number of intrinsic carriers, I think this is the last slide of this lecture. The number of intrinsic carrier means concentration of the carrier, concentration of the free electrons, Ni, and relative mobility is the micro n mu n. So it's the mobility. It shows the number of electrons, number of free. This property shows the number of free electrons in a cubic centimeter material, and this shows the capability of the electron to move faster. Okay, the flow of current in the material is due to the applied external voltage. Yes, if you apply external voltage, then the flow of current is possible. The number of free electrons in the semiconductor under this external voltage is called intrinsic carrier. So this is Ni is the number of free electrons, Ni. The more the number of free electrons, we understand that there will be more conduction. So intrinsic carrier Ni is the concentration of the electrons per cubic centimeter. Okay. So for germanium it is 2.5. Then this one for silicon is this for gallium. So we can see here the germanium has higher concentration value as compared to the silicon, and also as compared to the gallium arsenide. So we can other hand we can say that the gallium arsenide has very low carrier concentration. It means it looks like that gallium arsenide is not a good material, and here it looks like that the germanium is a good material because it has concentration density of the free electrons. The higher, as we can say, is higher. So straightforwardly, if we see this table, then we can declare it looks like the germanium is one of the good material. So the value of Ni is highest in the germanium and lower in the gallium arsenide. Apparently, it looks that germanium is the best, but it is not. But it is not the case, because we have also some other factors that contributes in the conduction, and one of the other factor is, as I said before, is the relative mobility, is the mu n. So what is the relative mobility factor, centimeter square? So what is the relative mobility factor for germanium? 3900. So highest is for the gallium arsenide, 8500. So here it looks like that gallium arsenide is having less concentration, but at the same time, if it is less concentration, then its mobility factor, I mean the movement of the free electrons, is very high, is 5 times high than is more than 5 times higher than the silicon. So this property shows that gallium arsenide here is one of the good material if we want, if we wish that electrons in the crystal moves very fast. It has very fast mobility factor. So if the mobility factor is very fast, it means that it has capability of making flow of current very fast. So if we combine these two properties, we will find that gallium arsenide is good if we want to make a semiconductor device faster than the germanium and the silicon. The value of Ni is highest in the germanium. Okay. So, however, another important parameter for the conductivity is the relative mobility of mu n of the free carriers in the material, which indicates the ability of the free carriers to move throughout the material. So table right about this one shows that the free carriers in gallium arsenide have more than 5 times the mobility of free carriers in the silicon. So if we want to make a fast device, silicon is not a good, germanium is also not a good, but gallium arsenide is good. That is the reason this shows that gallium arsenide electronic devices have higher operation speed that can be up to 5 times those of the same devices made from silicon. This is the reason in the application where high speed current flow is required, gallium arsenide is taking place in the development of the new electronic devices. So nowadays, the devices are tried to made from gallium arsenide, but the devices made from gallium arsenide is expensive, okay, due to the processing. Uh, I mean, it is expensive right now. Maybe it will become cheaper in the next few years. Okay, this is the end of this lecture. We have gone through only 8 slides. So see you if you have question. I will have a question answer session soon. So see you. Bye bye. Allah Hafiz.